Welcome to the AI in Manufacturing podcast here on Industry4.tv. I'm your host, Kudzai Manditereza, and today we will discuss the edge architecture for integrating industrial AI into control systems. And my guest on this episode is Garcia, who is the Director of Data Intelligence for Industry at Vicomtech. And welcome to the show. Thank you so much for taking the time to join us today.
Hi, thanks for inviting me to the interview. Okay, so yeah, my name is Andrea Garcia. I work in Vicomtech. We are a research center in Spain, in the Basque Country, very close to the France border. And what we do here is apply research. We are in the middle between universities and industrial needs, and we apply knowledge and technologies and scientific advancements to help companies with the problems. So, in my case, at the Data Intelligence for Industry department, we try to gain access to industrial data, to visualize it, analyze it, and to apply different artificial intelligence methods and algorithms for predictive maintenance, scheduling, and optimization of different processes, manufacturing lines, and to try to help companies to increase their competitiveness.
Awesome stuff. All right.
Mm.
So you developed this project
Mm.
about edge AI and architecture for integrating industrial AI in control systems on the shop floor. And I wanted us to start by really unpacking that specific project. So maybe let's start right at the beginning.
Mm.
I would like to find out what are the pain points or operational friction that you
Mm.
observed at the plant
Mm.
floor that sort of like led you to pursue this edge
Yeah,
driven architecture.
yeah, from my background, several years ago, I worked in different domains in the tourism and cultural heritage domain. And when I started working 7 years ago within the Industry 4.0 area, and I first went to companies, I remember that it was quite difficult to gain access to data. PLCs where they were quite close. You have to use implementation of the X7 protocol or semantic net software running on a computer, and it was quite difficult even to gain access to data. And I started realizing that was something hard that has become easier and easier with OPC-UA, Kware, and different technologies. But for me, I will say there was a project where we started working with the maintenance service of a big company, and they have in a big industrial facility in a corner, they had a SCADA system that was governing some ovens with that were working 24 hours, 7 days per week, whole year around, with a very SCADA style screen with all the data that was showing there, but no one went there to watch the
Mm.
data. Data was stored only in that computer, and it was impossible for them to use that data to identify problems that they were quite sure about that were happening, but it was impossible to stay 24 hours a day in front of the screen to get access to the data. And that's when we realized that the other architectures and were required to gain access to that data and to put data in to empower people at the factories at different levels, maintenance services, operators, engineers. Everybody can get value from data.
Awesome
Mhm.
stuff. Yeah, data accessibility, as you mentioned, is kind of like really a big challenge for a lot of enterprises and some small manufacturers.
Mhm.
And but you took it a step further by
Mhm.
enabling AI, and kind of like
Mhm.
I would like to believe that your approach there was to try and democratize the
Mhm.
access to not only data but also AI, right?
Mhm.
building this edge architecture for AI.
Mm.
So maybe if you could speak to us about how does your approach
Mm.
specifically for small manufacturing companies who may not have the skills
Mhm.
for AI implementation, how does
Mhm.
your architecture sort of like make it easy, or rather
Mhm.
make it easy to adopt this
Yeah.
industrial AI?
First of all, this architecture is based in microservices, in Docker containers, so it's quite modular. So you can change and swap the different modules for any tool you want, and it's quite a couple. We use a broker for messaging, and this makes easy to start small and to increase and to update while or when your requirements need them. So here we also for some of those modules we were aware with people of the companies nearby that early adopters within the companies or people with some technological background or maybe personal interest, they saw us some solutions with Node-RED and they were able to do quite complex things without knowing any Python code or any computer science background. So we started to use this type of solution as first choice for some of these modules, and then when the situation requires it, we can program custom modules in Python or any other language. And here what we do is to decouple the steps of this type of processes. So this allows you to start with the functionalities you require. So the first one is to access data, and we have like in the first step of the architecture module that from one side connects to the industrial equipment. It could be a line, a machine, a SCADA, a PLC, using OPC-UA, Modbus, or any industrial protocols. And at the other side, this module acts like a gateway that translates this data from the industrial protocols to MQTT, and the old data is sent to the MQTT broker, and data orders, writing commands, they are also received from the MQTT broker and sent back to the industrial equipment. And as I said, this module, it can be done with Node-RED. It could be a solution based on Kepware. It could be a custom solution based on Python or any other languages. Then once the broker receives this data, we start developing different further steps. The next one will be just to store that data. So we have like we call the egg writer that at the end it's only a, a script that could be also in Node-RED or in Python that subscribes to the data topics from the MQTT broker and stores them at the database. Here we use the time series database to store all this information, and we decided to use a timescale. Then we have another module to visualize data. Here we choose to use Grafana because it was also quite widespread and is easy to use without or with low level coding requirements for final usage to generate dashboards and as a way to be able to access historical data and see what was happening in a certain moment. And this Grafana or dashboard, they go against the database. And this could be like the first, the minimal step where you are able to have access to your data and to visualize it to see what's happening. And then when the next step would be just when you want to create a custom alarms or notifications. Here you could use a Grafana custom engine, or you could start playing with first artificial intelligence modules or algorithms where you can uh, have access to the MQTT broker where you can read real-time data, and then with this data you can call your algorithms. It could be value by value. You can generate time windows. You can store all the data from one manufacturing order from one cycle of the machine, whatever your needs are. You can generate a script. Usually here, this is a Python script where you gather all the data you need. You call the model, and then you send back the output of the model. You send back it to the broker. That could be an alarm. It will be a parameter of the machine that needs to be adjusted. It could be some new tag about a manufacturing order that you want to be stored at the database. For example, I don't know, the energy you have consumed or the quality expected or any other thing, or the time to live, depending on the use case. And with this setup, what we have realized is that we have the flexibility to give response to several use cases, and as we can update all of the parts, we also can scale very easily to different use cases. And being everything being Dockerized, it's the learning curve. It's very small, and it's very easy to get a project running and start having data and having some real utility for final users. Mm-hmm.
Awesome. So, I mean, I will sort of like, before we dive deep into, the architecture, I've got some, questions that I want to sort of like get some clarity for you, from you on. So basically what you are enabling here is that, industrial AI, at the edge on the shop floor. And typically you have got, some companies that run AI in the cloud, and then you have, obviously company traditionally they run logic in the PLCs. So you created this, layer for control, in the above, your control systems, and also at the edge. So I guess my question would be, what to you, what specific scenarios kind of like, make that edge intelligence outperform either cloud-based modules or logic that is running in the PLCs?
For me, regarding the cloud, I think that could be something that is very cultural or depending on the geographical area. But here we still face a lot of the companies. They are quite reluctant to integrate data from the shop floor with the cloud, and maybe for privacy concerns, from security concerns, but also from the infrastructure part, in order to get a network that allows you to have all the traffic that can be generated. It needs some upgrades and different things. And the cost of the cloud is variable. Even for small use cases, you need some services that you have to pay, and for a long time, or the whole life cycle of a machine or a line or a factory, it's difficult just to have that up front. And regarding the PLC, it's true that PLC providers, the software has improved a lot and it's more and more open, but still it's kind of marriage. So if you start doing all this intelligence within the PLC, you are like a prisoner in a closed environment. You do it the Beckhoff way, the Siemens way, the Wiener way, and you can get the advantages of all the general artificial intelligence tools that are being developed at a really is very big pace on the outside. So I would say that those are the main general advantages that you gain in the middle.
Okay, perfect. So now I want to come back to sort of like your edge AI architecture and really understand some of your architectural, design, choices. So to kind of like recap, you've got this, microservices-based architecture primarily, and then you develop components for connecting to your field equipment, Docker components, and then you've got an MQTT broker acting
Mhm.
as a sort of like decoupling, and then
Mhm.
you then have your data storage and also some AI models. So
Mhm.
first of all, why did you choose this decoupled
Mhm.
architecture and
Mhm.
used sort of like MQTT as the messaging backbone? What
Mhm.
advantages do you think that provides?
Yes. Here, for most of our clients and our use cases, here we are talking about small data problems. Here, even if this can scale to whole factories, we start with a machine, a line, something small that it's not generating so much data that the MQTT broker gets saturated. So it's MQTT simple, easy to start, easy to understand. It doesn't require a lot of resources. So we think that for this type of environment, it's it's very good approach with a quite good security level if you just follow the best practices. And that if you later you need to scale, you can swap the MQTT broker with Kafka solution or other types of brokers, or even from an open source broker to a commercial broker, and you get like more capabilities. And we think it's a good starting point. And yeah, well, that was the main reason we choose MQTT. And then when we start getting aware about unified namespace and different architectures and platforms that were being suggested, they also fit in these use cases, and we think that it's a proper way to go. Mhm.
Awesome. I mean,
Mhm.
speaking, you raised the point about open source, kind of like having this open
Mhm.
architecture. Kind of like leads to my next question to say, did you kind of like make a conscious decision to only use open source
Mhm.
components in that architecture?
Mm. No, it's more a restriction from our client, because here what we're doing with we're in charge of the research project. We propose an architecture. We validate it maybe in the lab. A lot of the times also in the shop floor. But then we transfer the solution to the companies. So some of them they have no problem, and they already use some commercial softwares, and they want us to use that software. For example, gateway for the gateway, or they already have maybe an historian, or other software they could be using, and we adapt to that software. But other companies, mainly small companies, they don't want to go for a commercial license and solution if they don't require it. And that's the main reason we choose the open source alternative, because at least when we were like looking the commercial environment, in most of the situations, the license, they are quite affordable if you use quite few data points, but they are not big fans of getting you allow for a big monitoring, or a scale, and cost can increase a lot if you further on you want to scale that solution that was started just with a machine, and you want to scale it to the shop floor or any solution. But
Yeah.
as I mentioned, these modules, they can be swapped by commercial solutions, and for us it's more a decision about each of the customers. Mhm.
Yeah, absolutely. Yeah, I
Mhm.
mean, I think, I mean, as you mentioned, like that's kind of like one of the biggest benefits of you of kind of like adopting this open ecosystem where
Mhm.
you're able to swap components, whether it's a
Mhm.
commercial, as long as they kind of like are using
Mhm.
open interfaces for communication.
Mhm.
So I think that makes a lot of sense. I
Mhm.
mean, as I was kind of like going through your paper, I also noticed that you sort of like made a decision to change. Initially, you had used InfluxDB as a
Mhm.
database for your architecture, following the popular Ming
Mhm.
stack.
Mhm.
and you swapped that for TimescaleDB. Could you
Mhm.
kind of like explain to us the reason for that
Mhm.
change?
Yeah, for us, there were like two main reasons. It's true that for me the main one was the learning curve. I mean, at the beginning we already have some projects with Influx, another one with traditional databases, and then you have to learn the Influx way of do things, the Influx way of querying, and that makes difficult for us to use it this technology in the project and to transfer it to companies. Uh, you can find people aware and quite with quite enough good expertise about SQL in most of the companies, but it's not the same about Influx. And with TinyScale, we have the best of all the worlds. We have with the same database, the same backups, the same technology. Uh, you have traditional relational databases. You could use like Mongo document JSON databases, and we have the time series functionality. And then when we start analyzing and developing with TinyScaleDB, for us, it gives the three main functionalities we require to time series databases. The first one is the summary, the visual summary of data. When someone asks you, okay, I want to visualize all the information of last week, then TinyScale it already has several different algorithms like LTTB or different sampling algorithms that before we had to implement them on the backend, and now you can ask directly to the database to generate that visual summary that respects most of the outliers, and it gives you, instead of 2 million points, just 2,000, 3,000, the number of points you ask for, and it's good enough to explore visually data, to do more tune in, tune out, till you find that certain moment or that situation just visualizing data. And then another problem that we faced with the first project was that once the project, the lab validation or the validation was over, uh, all the database filled with data quite fast. So clients were asking, were saying us, okay, I gave you or provide you virtual machine, but now the disk is over. There is too much data. What should I do? And then with TinyScale, the data aggregation to generate views that instead of using raw data, you can generate different levels with raw data, minute, 5 minutes, hourly data, daily data. It's very easy and efficient. And then the data retention policies, it's also very easy. With just one query, you can decide that each of the views it's going to store only data from the last week, month, year, whatever your requirements are. So with these three functionalities, all the time series data management gets very easy. And for us, that was the killer point. And then it's true that TinyScale, I think that's my personal opinion. It's a life project that they keep the open source nature of the project. They keep improving it, adding new functionalities, and well, I'm quite happy about the option we did. Mhm.
Oh yeah, that's super interesting. Yeah, I mean,
Mhm.
I've also recently, started to explore timescale,
Mhm.
DB, so I can really, vouch for some of this stuff that you are
Mhm.
mentioning. And it's interesting that you mentioned that it's not only just about the query language, it's also the data model, it's also
Mhm.
the infrastructure, the platform that you can put some plugins that help you with
Mhm.
all this kind of stuff. Because
Mhm.
I met the team from Influx at Hannover Messe, and they told me that they're with Influx 3 now they're
Mhm.
supporting standard SQL query. They're moving away from the Flux, so which is a
Mhm.
step in the right direction. But still, I think we still have like sort of like a limited data model, as it were.
Mhm. Mhm.
So that's super interesting. So maybe let's
Mhm.
kind of like go into the AI, aspect of this
Mhm.
architecture, and I want to know kind of like what types of AI algorithms are typically integrated into this architecture? Maybe if you could share some
Mhm.
few practical use cases.
Yes, I will say that first steps we could use a artificial intelligence word, but more than that, they are like custom alarms where you can, as you have access to all the data you need. It's very easy to implement uh, custom logic that access 3, 4, 5, 10 variables, and then it reflects the business case or the problem of the factory. If this variable is in this state and this one is in this range and this one is in this range, just rise an alarm or do whatever things. That those will be like the first advantage is that you can do it very fast and easily. And then when we start with the more advanced problems where we want like predictive maintenance or analyze the if there are some errors or predict quality prediction. Here, what we do first, we use all the architecture to uh, to store test data at the database, and with that we take out the data that we know that it's proper data with all the metadata. We generate exports with CSVs, and then with that data, we follow the traditional artificial intelligence flow with data scientists analyzing them, taking some hypotheses, developing different models, measuring the accuracy of each of the models till they get to the final model. And then with that final model is the one we integrate in a Docker container, and in that Docker container, we connect it to the MQTT broker so it can read real-time data from the broker. And then, depending on the use case and the algorithm, when it has the enough data to feed the algorithm, it executes the model, takes the output, and reacts according to the output. And that's like the second step. And then in the final step, that's something we are still researching about it, and we are working on that. We integrate MLOps operation. So we have different modules that are looking for data drift, for accuracy loss of the models, and then when required, they launch again all the training flow of the algorithms, and if the new algorithm is supposed to be or gets an improved accuracy from previous version, just the new algorithm is launched to production, and we keep all the traceability of the data and the algorithms that's been running. And this will be like the three steps of the artificial intelligence introduction. And depending on the use case, the model is different if we are working with high frequency data or energy data, or we are just having the focus on some variables within the process, and then we will use traditional machine learning, artificial intelligence methods, deep learning, whatever is required.
Awesome. I mean, couple of questions there. First of all, so you also use sort of like that, architecture for not for training data and also for inferencing. Is that correct?
Yes, here our idea is just to do the training offline, like in a different with a different team or different situations, and then integrate the trained algorithm to integrate it on the architectures. But it's true that when these projects they go into production and time goes on, sometimes the models need to be updated, and the clients ask us also for a solution to this situation. So that's why we are working also on extending that part of the architecture.
And then I'm not sure if you on the use cases you mentioned that you also have sort of like situations where you are writing information back into, the control system. So it's not only prediction, but you're sort of like closing the loop. And I sort of wanted to get your sense on like the maturity. So there's some companies that are sort of like, implementing a closed loop AI, driven control system, but some, companies feel AI is not mature enough to be able
Yes.
to take decisions on their own. What is your view on that?
For me, our reality is the second, the second way. Usually, if it's a process or something more complicated, we can generate like dashboard or custom web applications that acts as decision support system. In those decision support system, you could provide your opinion or the output of the algorithm, and you can show the button to send the command, but you can't send the command directly. So you expect someone to pass the button from you or to go to the machine and use the traditional HMI of the machine to perform the action. But that say, it's also true that for machines, not for lines, they are asking for some use cases, and they are asking also to integrate intelligence on those machines where you have a machine that it's maybe even if now it has buttons, you can control the machine using OPC UA or similar algorithm. So you can generate this gateway on top of the machine, and you can control the machine using the gateway. And in those cases, clients allow us to remotely control the machine, because sometimes remotely means a screen close to the or attached to the machine, but in the middle you have this HPC or H hardware that is running all the logic and all the containers, because just having this intelligence, it increases a lot the value of the machine, and the data you can later use to analyze your process and to compare a lot of things. And in these situations, we have the permission to control the machine directly.
Awesome stuff. Yeah, so maybe let's move on to real world, deployment and some learnings that you got from that. So you actually validated your architecture in a real world environment, in a vacuum control scenario. Could you kind of like walk us through that use case on exactly how your architecture was validated?
This case is about this intelligent machine I mentioned earlier. It was a traditional leak test machine where the first step is was to generate the vacuum, and then this machine was based on with helium. So if the vacuum is properly reached, the measure you get it's very very exact. So in the traditional workflow, the installer of the machine they do some trial and error phase to set up the machine, and the vacuum has two different pumps. The first one it's like a bigger one, and then once you reach a certain amount of vacuum, you need like the secondary pump that gets that has higher accuracy. And the times for this vacuum to start was set up by the operator. This trial and error that it takes time, and it was not very very exact. But the problem here was that the real-time data was shown on the interface of the machine, but it was not actionable. It was only within the life cycle of the PLC. So here, what we do was to put this architecture on top of the machine. We ask the machine provider to generate an OPC UI interface, so we have access to all the variables of the machine. That here was the value of the vacuum, and then the operations that were available at the HMI to start and to stop each of the machine, and the security step to close the BOS and all the related things. And then in this gateway, we model the machine as a black box with all the data that was required and the commands that it was accepting, that to start the test, to stop the test, and all the information that was required. And on top of that, we put the writer I mentioned before, the Grafana dashboard, and then the artificial intelligence model. So on the first step of the project, we use this architecture to generate a very vast data set in automatic mode with different times, different parts, and we get a big data set to analyze the evolution of the vacuum through the time for each of the tests. And we also have like the part in regular conditions and in wet conditions to see the evolution of the data. And then on top of that data, we created a couple of artificial intelligence models, and in this case they were not very advanced because the curve of data it really so it was a clear view of the proper moment to start the second vacuum pump, and then at the end of the curve it was possible to see when was the stabilization point of the curve. So instead of defining on the setup as a parameter the starting and the ending time of the pumps and the test, in real time the algorithm reads the value of the vacuum and decide when is the right moment. And we also generate like a signature of the wet part error. So if in real time we detect that the expected data was different, we could also identify that there was an error and just stop the test and raise an alarm on the machine to say, okay, something is happening, look for the part, or maybe something unexpected is happening. And that was that part. And then there is another use case that I mentioned that was just to empower maintenance team on the first use case I mentioned. And then in that situation, what we did was to train the maintenance team to use these Grafana utilities, so they were able to generate custom alarms or custom dashboards to try to confirm the hypothesis. I think that maybe when this is valve was supposed to be closed, there is still some air flowing around. When this oven is stopped, there's still some consumption, and maybe this is happening and this is not. So we empower them to get those tools, to develop them those tools, so they could operate them through the time, and they were able also to analyze a problem. Maybe if when someone told them, okay, there was a problem last weekend at noon in this machine, they could see what was happening and identify the error. And for those use cases, I think these architectures empowers them to perform better their tasks and to propose optimization at the factory floor that could be quite relevant. Mm-hmm.
Awesome.
Mm-hmm.
Thank you for sharing those use cases. So let's kind of like move on to standardization. I mean, one of the big challenges, sort of like with a lot of companies, as they implement initiatives like data-driven manufacturing or AI implementation, is lack of standardization, right? You've implemented this solution in one line, but you can't replicate that on a second line because there's no consistency in how all these systems present information. So one of the projects that you and your company and your institution really invested in is the asset administration shell for interoperability. So maybe first of all, for our audience who may not be familiar with what asset administration shell is, could you start by kind of like giving us a brief description?
Yes, the asset administration shell, it was coined by the Industry 4.0 movement, and I don't know if you're aware of the RAM architecture that it's evolution of ISA 95 for the Industry 4.0 world, where you have like 3 axes, like the traditional IC 95 as, then the whole life cycle of the product from designing to recycling, and then the different information layers. And the asset administration cell was like the communication format between the layers, and it has become the standard from for the digital twin, and it's promoted by the IDTA, that is the Industrial Digital Twin Association, which we are member of. And here, the digital twin is a term that is too much used. So I will say what is understood by the digital twin, that here is when you only have like the real world, and then the digital world, and they are connected, you have like a digital model. When you only get data from the real world to the model, it will be like a digital shadow. And then when there is like bidirectional flow of data, you can get data from the real world to the digital world, but you can also send data from the digital world to the real world. There you have the digital twin. So this is the meaning of the digital twin, that it's been standardized here. And the asset administration cell, the main idea is that each asset could be a product, a process, machine, an algorithm, has an ID. In the case of product, it's a QR code, and in that code is linked to a unique URL, and there you have all the data related to the asset. The most simple way is a product where you scan the QR code and you go to the information sheet of the product. And then there is very few fields that they are mandatory, and then there are several submodels that each of the submodel is focused on certain aspect of data. Some of them, they are like the digital product passport, the digital nameplate, but you can use some of the submodels that they are being standardized, or you could generate your own submodels that they focus on the data and the methods that they are relevant for you. And then, of course, you can properly model and identify each of them, which type of data, so you can generate tools on top of them. Mm-hmm.
Yeah. And so maybe to make it all concrete for our audience, could you kind of like describe how asset administration shell could be used with your edge AI architecture?
Mm-hmm. Yeah. Here, I will give you my point of view. When we are talking about internal communication, the AAS is not so relevant, because you own the whole setup. What is important is the model part. To when you define the black boxes of your machines or your product, that you get an agreement of what are the relevant the relevant aspects you want to model, and how you are going to represent them. Then if you have like 3 different engines, each of them with information in 3 axes, the speed, the rotation, whatever, that you standardize how you are going to address those information. And the closer your model is from already proposed standards, the better. But at least in your internal organization, that should be consistent when you from the gateway to the dashboards. So you know where everything is there. And I think that's the problem. That is the same for the AAS, for UNS, for OPCUA, for all the standardization efforts. They require you to do that. And then the main advantage of the AAS is that it allows you to gather all the relevant information about the asset, and that relevant information, it can be of different. There are 3 types. One is the type 1, that it's static information. You can think like a standardized zip file, where you have all the relevant information about the whole life cycle of the product or the asset. That will, in this case, a product, you could have designing the 3D models, the recycling information, the bill of materials, the product data. So it allows you to gather everything. So it's quite relevant to store that information, and our architecture could fit the AAS that will get more data from different systems uh, of the organization. And then when you have several organizations that they are going to collaborate together, that's where the AIS is required. So you can agree on the submodels, and a part of the format, the AIS also gives a tooling to show to share this asset administration cell, to generate data spaces on top of them, to connect them with the real asset in real time, so you can get the data from the AIS of you can get data of the physical asset, and all those things that are available in a standardized way with the AIS. I think that that's one of the main advantages you get there. Mm-hmm.
Yeah, I mean, what would be the difference between AAS and say maybe OPCUA companion specifications
Mm-hmm.
in the event that a company already uses
Mm-hmm.
OPCUA companion specifications, or they've got their own custom? Can you kind of like
Mm-hmm.
give us the
I think that's more the objective of each of the approaches. It's true that OPCUA is getting bigger and bigger, and its scope is getting from the shop floor to the cloud and taking more. But I think that still the core of OPCUA is the access to industrial equipment, industrial data, and that's where they are very strong. And in those situations, the connection usually is one-to-one or one-to-few. But you are not supposed to get access to the machine through the OPC US server for everybody. So I will say that that will be the main use case. And then with the asset administration cell is the other way around. You have like this virtual representation of the machine that can be connected to the real asset or not, and it's on the IT world. So a lot of people can connect there. You can control which submodels are open to everybody, which submodels they are open just for certain users. You can host it on the internet. You can host it on premise, on the edge, just close to your factory. So it gives you several advantages, and I think that they serve a different use case. And say that, I think that a lot of companion specifications and submodels, they should be equivalent, because the modeling work has already been done. And if something has been relevant for the OPCUA community, probably it's also relevant for the rest of the communities, because the industrial asset they represent, it's the same.
Oh yeah, absolutely.
Mm.
Great stuff. So yeah, I mean, I wanted to sort of like talk about your other interesting project,
Mm.
operator as a service. But before we jump into that, is there anything else maybe you want to talk to us about the edge AI architecture? Did we miss anything?
Mm. No, just I think that is it's evolving real fast. I just think in life, I think that there are two trends that they could arrive and can be very interesting. One is the use of microprocessors with TinyML and different approaches that can generate value with very low investments, but they already, even if they are not too powerful, they are powerful enough to analyze data in real time. I think that they could be a solution for a lot of situations, maybe not for critical or security data, but just to add additional data that could improve the operation of lines and factories. And the second one is that with the language models and the MCPs and all this wave or tsunami that it's coming, I think requirements will increase, and I think that's quite interesting research field nowadays. But in quite short time, it could be around a lot of us.
Yeah,
Mhm.
absolutely. I mean, that's certainly one of the things that I'm going to be sort of like looking forward to see from your side, how you're going to, approach
Mhm.
these AI agents, MCP world,
Mhm.
integrated into your AI architecture. So
Mhm.
certainly interesting. I'll certainly look
Mhm.
forward to that.
Mhm.
So, I mean, just want to take the last few minutes to talk about, your other interesting project,
Mhm.
Operator as a Service. I think this is what you were also demonstrating at Hannover Messe this year. Could you kind of like tell us, about, what is the vision for the project? What is the problem that you're solving in there?
Yes, here in this research project, we gathered together several folks here from Vicomtech, and we thought about a fully automatized factory or dark factory where little human intervention is required or no human intervention is required at all, but still unexpected things happens, and if there is no one there to solve them, they can provoke the whole line to be stopped. So we thought about how we could solve this situation with the technologies we work, like digital twin, computer vision, robotic, autonomous mobile robot, data analytics, and here what we thought was a scenario where in these factories you are not going to require people paying attention full time, but you could have like a pool of remote operators that in case of something unexpected happens, they get notified. So they connect remotely to a digital twin of the factory. They have enough information in the virtual world to analyze the situation, and if they can solve the problem, to get remote control of the asset to solve the problem in the digital world, and then when they are happy with the solution they have proposed, just send the command for the whole setup to be executed in the real world, and they can keep on the helping another factory or performing any other task they are doing. And that's what we work with, and then we solve it at Hanover Mess this year.
Awesome. I mean, is there any, particular architectural approaches or standards or any technologies that you used to solve that?
Here, we follow a similar architecture of the previous one, where we model each of the stations of the line as black boxes, communicating either using OPC UA or MQTT, and then we deployed like the brain of the system, orchestrating all the stage of the manufacturing line, and the processors, and giving the orders to each of the line, and then each of the black boxes, the robot, it only has to keep the contract and to react to that data the black box is expected to send and to receive, and that allowed us to design the steps of the manufacturing lines where the errors could happen, and then to give the remote operator the possibility to solve the problem and to say, okay, now go to this state and keep working on this step.
Awesome. Yeah. So, I mean, to conclude this session, I mean, as you mentioned, things are moving so fast in the AI world. It's really hard to sort of like predict what's going to be happening in the next few years or months. But as a tradition, generally in this podcast, I like to ask our guests to kind of like give us a sense of what they see as being the future of AI in manufacturing. What are you excited most about in sort of like in the future?
I thinking about that. I thought about three main points. The first one is data availability. That I think that now with UNS and all this movement, people is getting aware that the value you can get if you put at the same time at the same place information about the ERP system, the SCADA system, the MES system, the shop floor, the operators, the raw materials. You can unlock a lot of value with artificial intelligence, having the right data in the right moment. And I think that we are going to see more and more advanced applications based on this data availability. Another point that is related, I think it's high frequency data. We work more and more with projects where we get data even up to kilohertz frequency, that it allows you to get a deeper view of the processes. So you can perform different types of improvements and optimization, error predictions about the processes. And I think that is something that companies are moving onto this because it gets another standard of knowledge about your process. And the last one is all this LLM, NCP, agent-to-agent movement that I I think no one knows what's going to happen, but it's moving so fast that every 3 months you get surprised and amazed of what's been proposed, and all of us wanted to try and to see the possibilities is open. So what can be the future applying them to our factories.
Oh, yeah, absolutely.
Mhm.
I mean, and thank you so much for really taking the time to join us on the show
Mhm.
today and share your insights with the audience. We're
Mhm.
going to provide links to the material that we referenced here.
Mhm.
Maybe before we close this session, any last words to our audience? Where can they find you? Is there any special, project or website
Mhm.
or link
No,
that you
yeah.
want to?
Please feel free to contact me through LinkedIn or send me an email. And really happy to collaborate with any research projects or any activities. I think that it's really nice moment to be on this community, and I think that yeah, very really nice projects they are available out there, and really willing to collaborate on them.